Welcome to Lecture 8. We will be talking about alkanes. So the last lecture you learned nomenclature. So hopefully you have learned how to name the alkanes. And this one we're going to be talking about conformations of alkanes. And we'll be talking about the acyclic compounds. So we are going to work your Povel Activity 5A. We will talk about how you can see these conformations with your eyeball when you look down the carbon-carbon bond. And when you do that, we're going to be drawing some Newman projections. So you're going to have to learn how to draw Newman projections. We're going to look at some graphs and talk about stability of these conformations. Now, a conformation is like if you are standing versus you are sitting versus you are lying down, okay? It's still you, but when you're in these different positions, you're in different conformations. When we go to Chapter 5, we're going to talk about configurations, and that is a different compound, okay? That's a different compound, and you're going to see that they are stereoisomers. So they're different compounds. They're stereoisomers. You learned from a few lectures back that stereoisomers have the same molecular formula, but they have the same connectivity. But a stereoisomer has a different arrangement in space. Okay, so we'll learn about configurations, but right now we're talking about conformations. So conformations are the same compounds, but they are in different positions. All right, so you're responsible to read your textbook and to work through the slides. We're going to go ahead and start on the Povel activity. Okay, so let's work Model 1. As I draw Model 1, you can go ahead and start reading the questions and thinking about them, and then we'll talk about it. Now, as I draw compounds A and B, what are their relationships? Can you look at them and figure out their functional groups? Okay, and then the dash is the bond going into the page, which is back behind you. Okay, so this line here means it's in the same plane. So it's in the piece of paper like, okay? So I will highlight that on these molecules so you can see the plane. This is where molecular models are helpful as well. Okay, so we have a few definitions that you have to know. constitutional isomers. That should not be a new term. They are atoms where they're connected differently. Atoms are connected differently, but they have the same molecular formula. Okay, that's not written there, but it's true. Conformational isomers, and they are atoms. Of course, they have the same molecular formula if they're isomers. They're atoms that are connected the same, but they differ around the bond rotation, around the single bonds. So single bonds can rotate. So this blue line that I drew here has free rotation. We looked at where alkenes do not get to rotate, and you have some restricted movements as well in your cyclo compounds. So we'll be looking at those. Okay, let's answer question 1A. For the structures in Model 1, write down the order of the atom connectivity for compounds B and C. Ignore the hydrogens. Compound A is given as example. So A, we have carbon, 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 O. So we have carbon, 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 O, and that's your example. Okay, so for B, we have carbon, carbon, O, carbon, 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 O, carbon. And compound C, we have carbon, 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 O. Okay. Is the order of connectivity the same for structures A and B? No. And you can look at A as what? An alcohol, and B is an ether. Is the order of connectivity the same for B and C? No. C is also an alcohol. Is the order of connectivity the same for structures A and C? So if you look at A and C, did you write yes? Using the definition of constitutional isomers, indicate which pair in the model are constitutional isomers. So did you write down A and B are constitutional isomers? Okay, in Model 2, Model 1, what does a wedge represent? So you just write that down. Means that the bond is coming out of the page. What does the dash represent? The dash is that the bond is going behind you. It's going in the back, behind the page. Compare structures A and C. We're comparing A and C. What does the wedge, or are the atoms connected in the same order? We said yes. What is different between the structures of A and C? Okay, so if we look at the first carbon, they're the same. We go to the next carbon, they're the same. We go to the next carbon. The hydrogen's coming at you, the OH is going back. But it looks like that this bond here has been rotated. So the carbon-oxygen bond has been rotated. Is that what you noticed? Okay. Based on the definitions in Model 1, would A and C be constitutional isomers or conformational isomers? What did you decide? So A and C are conformational isomers because their connectivity is the same, but their rotation around the single bond differs. Okay, we are going to look at Model 2. we'll look at model 2 now. I'll let you go ahead and work that. Okay, as I do these, you might want to be asking yourself, what is different between these drawings? Because it'll be up to you to understand. Now these 3 wedges mean it's the same. It's kind of like the equal sign in organic chemistry. Okay, so the first set of structures are the wedge dash way to represent compounds, and these are just different ways to draw the compounds. The middle structure is called the sawhorse, and the last one is the Newman projection. And we need to be able to draw compounds using all 3 of these kinds of types of drawings, just like we did for the condensed formulas and the skeletal drawings. Okay, so this is a way to see conformation. Conformation is basically free rotation around the single bond. Okay, now question 3. In the wedge dash representations of ethane, how are the hydrogens drawn to show their spatial orientation? Okay, so the line, this line drawing, is the line is in the plane of the paper. Okay, so it's in the plane. And then the wedges are coming out of the plane. Okay. And then the dashes are going behind. Okay. Away from you. So the dashes and wedges are on the same side together, and so the wedges are on the same side, so both these hydrogens here are on the same side that are on the wedge coming at, and what's behind is on the same side. Okay, question number 4. Envision the wedge dash model where the carbon-carbon bond is in the plane of the paper. Use a pen to simulate the bond. Visually rotate the whole molecule by 90 degrees so that the carbon-carbon bond is now perpendicular to the page. Okay, so if you take this yellow in the plane and you actually take this bond and you turn it 90 degrees, it is now here. Okay, and this is the sawhorse. That's what it's talking about. On the sawhorse model above, write F for near the front carbon. So here's F, okay, and this is going to be your front carbon here. Okay, so there's your front carbon. And on the sawhorse model above, write B for the back carbon. So when you rotated this, this is your back carbon, and here's the B for back carbon. Circle the bond that was rotated by 90 degrees. This is the bond that was rotated 90 degrees. Okay, question number 5. The Newman projection, which is all the way to the right here, is the same as the sawhorse projection that has just been compressed along the carbon-carbon bond. How is the carbon in front represented in the Newman projection? All right, so the front carbon here that we made blue is this one right here. Okay, so that's your front carbon. And you have the 3 hydrogens that's coming off of that front carbon. How is the back represented? The back is represented by a circle. So this is your back carbon, okay? So this is your back carbon. This here is your front carbon in the Newman projection. Okay, number 6. 6A, from Model 2, compare the 2 conformation of ethane, staggered and eclipsed. Okay, so we're looking at staggered and eclipsed. What is different between these conformations? Okay, so what is different? This is a way to look at the dihedral angle. So if you're wanting to look at the dihedral angle between this hydrogen and this hydrogen, okay, that would be this hydrogen and this hydrogen. This angle here is the dihedral angle. And in staggered, well, the dihedral angle that you really care about is this one with this one. You have this one with this one, and that dihedral angle is 180 degrees. If you look at it here for H1, and then the first H, these dihedral angles here are like 0 degrees. They're eclipsed. So if you think of when the moon eclipsed the sun, you can't see the sun. So it's this dihedral angle that's being shown that this is 0 degrees. So if they're staggered, this means they have the greatest amount of dihedral angle separation. Once your group agrees on the above questions, discuss which conformation would be the most stable. Okay, so obviously with these groups that are repelling each other, the staggered is the most stable. And it has a dihedral angle of 180 degrees. Describe why the names staggered and eclipsed represent the forms above. And I always think of, like I said, it blocks out the hydrogens for eclipse. All right, so model 3. You can go to the next model now. And we're going to continue writing Newman projections. So the first one's a staggered. And in the staggered you have gauche, which has a dihedral angle of 60 degrees. And you have anti, which is a dihedral angle of 180 degrees. The next one is eclipsed. Okay, and then you have this defining a dihedral angle. And that is a representation, and this is the dihedral angle. Okay, so this is your model. So 7. Using information on model 3, identify the dihedral angle for the following. So if you have a staggered gouge, the dihedral angle is 60 degrees. So this is gouge. This is your 60 degrees. Okay? And it's always the staggered, and then there's the gouge. The staggered anti is this one right here, and that's the anti, and that's 180 degrees. Eclipsed has to use this Newman projection, and these are your eclipsed. An eclipse is 0 degrees. Okay, number 8. What is the dihedral angle between HA and HB? So between HA and HB, did you circle 60? Is this gouge or anti? That would be gouge. Okay, 60 degrees. What about B? What is the dihedral angle between HA and HC? Did you circle 180? Did you circle anti? Okay, number 9. A. A Newman projection is drawn by looking straight down a particular carbon-carbon bond. The carbon furthest away is drawn as the large circle. Okay, so the carbon further away is the large circle. Okay, while the carbon closest is represented by a small circle in the front. The carbon furthest away is a large circle, the carbon closest is a small circle, or the center of the Y shape. Draw a Newman projection of propane as viewed along the carbon 1, carbon 2 bond. Okay, and they want propane. And you do need to learn how to draw these. I'm going to show you kind of a quick way. All right, so propane, first of all, you'll want to draw your Lewis structure of propane. Okay, so I've told you before that you really want to draw good Lewis structures when starting to solve all problems. Now, I want you to get used to drawing this framework, okay, and this is your staggered, or you draw the eclipse framework. So you draw your front carbon the same way, but in eclipse, your back one goes here. So if you're going to the right, just stay to the right, okay? And this is eclipse. So this is always going to be your framework for drawing Newman projections. Now, what do you decide to put on the front carbon? Well, here they want C1. So label this C1, and then we'll label this C2. Okay? And then this would be C3. So draw a Newman. So your eye, to make you have blue eyes, okay, your eye's looking down the C1, C2 bond. So draw C1 in the front, and C2 is going to be your back carbon. So you can just circle that, and this is going to be your front carbon. Then add all the substituents. Now your lowest energy are your staggered, and so you see how this has H, H, H. There's 3 of these. So there's an H, there's an H, and there's an H. That covers your front carbon. And it's connected to your back carbon, this blue. And you get an H, another hydrogen. And then you want to make this a condensed formula, CH3. Okay? And if you did the eclipsed, then your front would be here. And you just make the front H, and then the blue you would fill in H, H, and then CH3. And I can make that CH3 black if that would make you happier. It's coming off the back carbon. And so that's how you draw a Newman projection. All right, so B, once your group agrees on the Newman projection drawing a propane, draw both a staggered and eclipsed. Okay, so there's your staggered and there's your eclipsed. Circle the form that is most stable. The staggered is the most stable, okay, because it gets these substituents further away from each other. Whereas eclipse, the dihedral angle is 0 degrees and it's right on top of each other. All right, now we're ready to go to Model 4. Okay, for Model 4, we're going to do something different. We are going to do a potential energy diagram. And we're actually going to do it for butane. So if you need to go and get your notes and slides, this is important. Ethane is not that big of a deal, okay? But butane is very important. So butane's so important that we're gonna change this model a little bit, and this is actually figure 311, page 164 in your book. Okay, and sometimes I've seen this potential energy diagram on like the American Chemical Society exams. Potential energy on your y-axis, and then on your x-axis you have this energy diagram. Okay, and I think it's important for you to learn how to read energy diagrams. Okay, so what I've tried to do here is I've tried to make these the same height. Okay, so I've tried to make those the same height. Okay, and then I've tried to make these the same height. Okay, and then this is your lowest energy. Now, sometimes you have to match these conformations with the energy diagrams. So here, the rotation is 0 degrees. This is your dihedral angle on the x-axis. So your dihedral angle at 0, it's 60 degrees. Okay, so have this. This one is at 120 degrees. This is 180 degrees. This one is at 240 degrees. We're just rotating that single bond all the way through. We're doing a full circle, 30 degrees, and then 360 degrees. Okay, so if you have butane, 1, 2, 3, 4, and we're rotating around the carbon 2 and the carbon 3 bond. So what does this look like? The first one is eclipsed. Okay, and so on all these eclipses, I'm just going to go ahead and draw the Newman projection here. Okay, so every other one is eclipsed when you rotate it, and this one's total eclipsed, and this one's total eclipse. So the highest here is total eclipse, and so this one's total eclipse, and that means it's the highest energy. All right, so you come here to this one's gauge. Okay, and this one would be gauge. All right, so those are gauge. So they're lower in energy. A gauge is a form of the staggered, right? So that's a form of staggered. That tells me what kind of framework I need. And then we have here, this is anti. That's a staggered, but it's the anti. So we'll look at that one. And then we have this here, and these aren't totally eclipsed, but they're eclipsed. And the reason why butane is so much more interesting is because you'll see this, and I'll make the carbon to the front carbon. And now, when you're doing this, let me tell you, it's easier if you just rotate one bond. So you decide if you want to rotate the front or the back. I rotate the back, okay? So then your back is this C3. Okay, so the back carbon's the C3. I'm putting that on each one of these. Okay. Now what I'll do is for C3 is what's here is you have the eclipse. So I'm going to put this in eclipsed. Okay. Staggered. I'm going to make a staggered framework. Eclipsed. Here's my framework. I haven't put my substituents on there. Staggered always goes like this. Eclipsed always goes like this. Staggered. Eclipsed. Okay. Now I get to decide what to put on here. So C2 has a hydrogen coming at you, hydrogen going back, and then the CH3. That's a CH3. So here, for eclipse, and it's total eclipse, that means this CH3 and this CH3 are on top of each other. They're eclipsing. So here's a CH3 there, and this is your CH3 there. So if you go ahead and put your hydrogen, 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 and then your back carbons have hydrogen and a hydrogen. Okay, so then if you rotate this, and we're just going to rotate the back carbon, so now we keep the front carbon the same. So I'm going to go ahead and put the front carbon on all of these the same. Okay, see how I have my CH3 at the top, and I have my hydrogens on my front carbon. So I do this for every one of them. And then what we're going to do when we go through this energy diagram is we just rotate that back carbon. So now we have the CH3 here, and now it's moved here. And I'll go ahead and put hydrogen in yellow. Okay, so this is hydrogen and hydrogen on the back carbon. Okay, so this is your dihedral angle, and that's 60 degrees. Okay, here we've rotated it, it's down here now. Okay, and you see that that is eclipsed. You see how that's higher energy than gauche, but it's lower energy than total eclipse. Why is that? Because the CH3s are bigger steric groups, and they are their electron clouds are interacting with each other. Okay, if we keep moving this CH3 here, now this is your lowest energy, and that's because the dihedral angle here is 180 degrees. So anti is your lowest energy. It's because these CH3s are as far away from each other as possible. Those methyl groups are very bulky. Okay, we're keeping moving the CH3. We're moving it here now. Okay, we're back to eclipse. You see the CH3 and the hydrogen eclipse each other. CH3 and hydrogen are eclipsing each other. Here, the total eclipse is CH3 and CH3 eclipsing each other. Okay, we move it back here. We're keeping moving the back carbon. Now we have gauche, because these two, our bulky groups, are 60 degrees. That angle's 60 degrees, just like it was over here. And then we move it again, and we have total eclipse because we've moved it all the way to the top, and they're back that 360 degrees of rotation. Now, Model 4 is asking you questions regarding ethane. So I will let you look at those, but I'm not that concerned with you if you don't want to answer those questions. For ethane. because they're ethane, they're hydrogen, so they're not that much different. But if I go on to page 56, it asks you to draw Newman projections for butane. Okay, so look at page 56, number 11. It tells you to draw the staggered Newman projection for butane, 4 carbons, is viewed along the C1-C2 bond, and a staggered projection viewed along C2 and C3. All right, so let's look at that. So if you did butane, okay, so let me go ahead and when you draw the dashes and the wedge, put them on the same carbon or same side. You see how these are drawn same side? Okay, they're on the same side. Don't do it like this. Okay, it'll mess you up. Don't do it like that. Do it like this. All right, and it says to draw a Newman Bond C1, C2. And they want staggered. So go ahead and draw your staggered. Okay, that's your staggered framework. And they want C1, so this is C1, and this is C2. Okay, so C1, you just draw your hydrogens in. Doesn't matter, they're all hydrogens. And then you go C2, and this you're going to want to make a condensed formula. Okay, so CH2, CH3, and then you draw the hydrogen coming at you and the hydrogen going back. Okay, now it also says draw it around the C2, C3 bond, and you want staggered. So once again, you draw your staggered framework. Okay, so there's your staggered framework. I'm going to clean it up a little bit. Okay, there's your staggered. And they want C2, C3 bond. Okay, so C2 is here, the front. And now we're going to make this a CH3. So you just put that CH3 there, and then you have a hydrogen coming at you and hydrogen going back, hydrogen, hydrogen, okay? And then on the green, you have the C3 bond. You make this the CH3. And I'm going to put the CH3 far away from that other CH3. And then you have this hydrogen coming at you and this hydrogen going back. You put it there. This hydrogen going back. Now, this is the dihedral angle here is 180. So what is that? That would be anti. That's going to be your most stable. Do these structures look the same? They kind of don't, do they? They're the same compound. Draw Newman projections for butane as viewed along the C2, C3 bond with dihedral angles of the two groups. So they're asking for eclipse, which we did right here. And they're asking for the gauche and eclipse and the anti. So you can basically do what we did here is question 12a. Identify which of the above Newman projections are staggered and which ones are eclipsed. Okay, so when you get that done, you can say, okay, this one's staggered. And you can see that all these are staggered. And then the eclipsed would be the eclipse framework here. Okay. Once your group has reached agreement on the Newman projections, discuss whether you expect all staggered forms to have the same energy. Well, you know that they don't, right? So the gauche is staggered. The anti is staggered. and the gauge is staggered. And the staggered is the steric repulsion of the dihedral angle. So the anti is lower than the gauge. So I wrote on my notes, anti is lower energy than the gauge. Would you expect all the eclipse to have the same energy? And the answer to that again is no, because you can see that you have total eclipse is higher energy than the eclipsed. And that's because these methyl groups are eclipsing each other versus a methyl and a hydrogen. Two methyls are bulkier. Which Newman projection would be the most stable? That would be the anti. You see it has the lowest energy. And this would be because the methyl groups are the furthest away. All right, so now you are ready to work the problems on page 57. Draw the Newman projections and maybe 58. So you need to be able to do those. So work on those.